3D printing and machining come together. This is a 3D printed part for a CNC machine tool.
In this episode, the winner of the Cool Parts Showcase for Best Production Part.
The Cool Parts Show is brought to you by Carpenter Additive. When it comes to managing metal powder, there is no one-size-fits-all approach. Stick around after the episode to learn more. I'm Pete.
I'm Stephanie.
Welcome to the Cool Parts Show.
This is our show all about cool, interesting 3D printed parts, and we have here today one of the winning parts in our Cool Parts Showcase from 2021.
Yeah, so Stephanie, a thing we love even more than brackets, CNC machine tools.
I think we love 3D printing more than that, but okay, go on.
We love 3D printing. This is a 3D printed component for a CNC machine tool.
This part was the winner in our Best Production Part category. We were looking for something that is currently being made or sold, and that's what this is. This adapter is produced by DMG MORI, major machine tool builder. They now also produce 3D printers, and we'll talk about that later. But this particular component was produced for the machining side of their business.
That's right. This is the AKZ FDS adapter, a component of a machine tool, DMG MORI machine tool, big name in machine tools. And this goes on a CNC, computer numerical control machining center, a sort of machine that does milling, drilling, and in the case of this particular machine, grinding as well. So this adapter helps deliver coolant, cutting fluid to the cutting edge on a machine that has all those different kinds of tools in play, a milling tool or potentially a grinding wheel, and this adapter directs the cutting fluid to just the right place for all that different type of tooling.
Right, so this is an example of additive manufacturing helping subtractive manufacturing, helping machining, but it's also an instance of additive manufacturing as a replacement for machining, because that's how this component used to be made, right?
Right, so the essence of this part is fluid flowing through it, fluid flowing within it, and it was made conventionally prior to additive, but often in cases like that, where it's an internal fluid flow component, it's made through assembly, like those internal passages are built in, the components built up around it. That wasn't how this was made previously. It was made through machining, and those internal fluid passages were achieved through drilling. Straight drill, straight hole from the outside of the part, holes that intersect to make those internal passages, and then the outside of the hole was plugged up. It was sealed so that just the internal passages are left inside. So this part, there is some assembly reduction as a result of additive manufacturing. There is lightweighting, but there's also the elimination of almost all of those external sealing points, because now those fluid passages are just printed into this solid part.
So I want to bring in one of our experts now. This is Hannes Ebers. He is a project engineer for DMG MORI's Additive Intelligence Department. So one of the things that this department does is look at different parts, customer parts, internal DMG MORI parts, and try to identify good use cases for additive manufacturing. So he can talk more about how this part used to be made before they identified it as an opportunity for additive manufacturing.
Before, it is a traditional milling part. So we haven't invented the ring completely new. So we had a block and created more ships than everything else. So most of the material, the metal from the block, is waste. And on the other hand, we need these media channels inside of this part. So we have to drill deep, small holes from one side, and from to reach the other end, we have to drill from several angles, and we need to clock most of the exits or starting points of the drilling holes. This is a little pain because we have more sealing points or connections what we have to clock than everything else. It's like cheese from Switzerland. More holes and more cavities inside of a metal part than everything else.
So I think that's a pretty good visual of what's going on inside of this part, the Swiss cheese analogy. And when you think of it in terms of subtractive manufacturing, like previously they started with a solid block of material, they were removing material to make those holes and then having to plug up the ends later. And now with additive, they can think more about building walls around the channels that they need and using less material, just putting it where it's absolutely necessary.
So that's right. They were removing material. They were putting it back in the form of sealing these holes. Let's talk about DMG MORI. Their equipment is most widely associated with material removal, precision metal cutting. But in more recent years, this company has also begun offering metal additive machines. So let's talk about how was this part made?
I think that's important, and that's a really cool part of this story, because this component for DMG MORI machining technology was made on DMG MORI 3D printing technology. So the specific printer that they use for these is the LaserTech 30 Dual SLM. So it's a selective laser melting or laser powder bed fusion system, and it has dual in the name because there are two lasers doing the melting of the metal powder to build these up.
So we have a system with two lasers. And we produce it in stainless steel 316L. This, on a dual laser system, takes approximately 57 hours. Still some hours, but this ring is not really small. After that, we start with depowdering inside of the machine. We open the doors, get out the part, and then the depowdering in a depowdering machine next to our printers start. Of course, this is really important because of all the cavities inside and the channels. It's really important to get rid of all the powder, because next step is the heat treatment. This is a quite big part with a diameter of 300 millimeters, so it has some residual stresses, and we want to get rid of them. And so for this, it's very, very important that there is no powder left in the channels. And after that, we go to our milling machine. So we use the printed or the print plate, the basic plate, for clamping. On the milling machine, we separate our AKZ ring from the solid support we have inside for depowdering and everything. So we separate that one, then we get out the plate and the rings, go to the bandsaw, cut it off, separate the ring from plate, and then we go back to the milling machine and start to work on the part again, finishing the part. Then quality control, and we have our final part.
Hannes mentioned depowdering, and that's actually a really interesting part of this. To make the depowdering step more efficient, they actually 3D printed another component that aids specifically in that operation. So here's another voice, another person associated with this work, Niels Niemeyer. He is the general manager of the additive manufacturing business for DMG MORI in North America.
Once we're finished printing the part, we are depowdering the build chamber. And so the designers came up with a very clever way of doing it. In fact, there are channels in the center of the sealing ring. And we can apply the vacuum of the machine, the vacuum hose, to those holes and extract the powder in a very efficient way. Now, this is sacrificial material, and it is not functional for the actual part in the end. So after we depowder the part in an efficient manner, we put it on a machining center and cut that ring out in the center. As well, we finish all the functional surfaces. So we depowder the part first, and then we finish machine the part in the final step.
There's something I really like and appreciate about this particular part. Like, we were looking for a good production use case of additive manufacturing, and that's exactly how DMG MORI approached the design and manufacture of this component. They thought through everything from how do we orient the part in the printer, like how should it be printed, to how are we going to remove all of that powder from these channels and let's add this extra feature to make that easier, to how are we going to clamp and fixture this in a machine tool for the finish machining. They thought through the whole thing.
Right, they saw this opportunity that this part could be better with 3D printing, but there was also this recognition that design and production are different, and they thought about them separately. Hannes has more to say about that.
You always should focus on the whole process. That is always important, what I see when I'm working with customers. We have a lot of customers from milling, or sometimes we have customers, they are just in printing, but the process is so important. In the first step, in the development phase, you should have or make some ideas about how to clamp the part, how to get out the powder. You have seen this solid support we have designed and not created automatically with a work preparation software tool, just because we have the process in mind.
So there was a lot of work that went into this part on the back end to develop it and to get it ready for production. But let's talk about results. How is this 3D printed adapter better than what came before it?
So the performance of the part is significantly increased by functionally integrating several components of an assembly into one print. And that way we're reducing the sealing points. And that way we can much better bring the coolant towards the grinding wheel.
So we had 15.6 kilograms from the traditional design, from the milled design. Now we have 8 kilograms. So we have a lightweight ring now. We had a lot of sealing points from all around the part. And so we reduced the sealing points from 46 to just 4 now. We have 4 sealing points. And we reduced the amount of parts we need for the assembly from 71 to just 5. But we have a little bit more. We have the channels itself. The initial design was just drilled holes, and so it wasn't really optimized for our flow. We have losses of pressure. And now we are optimized in a flow optimized design we have now. Another point is we have reduced commissioning, warehousing of all the different parts. The part is more simple now. We have, of course, a printed design, but we don't have the complex assembling process to have later our channels. And last point is another advantage. The initial design, the milled design, we needed special tools for. Longer drill tools, special tools are always expensive, and now we print the part, and the final machining on our milling machines, we can do that with standard tools, standard and so not so expensive tools.
All right, I think we got this. You start?
Sure. This is the AKZ adapter for a DMG MORI machining center, a machining center that, along with milling and drilling, is also capable of grinding, and that's what this particular adapter is all about. It's all about getting the cutting fluid, the coolant, to those different kinds of tools and mills and grinding wheels that might be used on this machine. This was made through additive manufacturing, but it wasn't always made that way. There was an earlier version of this adapter made through more conventional processes, and in the case of that earlier part, to get the fluid channels that flow through this adapter, that was done through drilling. Holes were drilled from the inside, they intersected to make these channels, and then all those entry points for all those holes were sealed up. This is a simpler design, it's a lighter design, and by being one piece and containing all of those channels, it eliminates almost all of those sealing points that had to be done just right, or else they were risks for leakage.
The 3D printed version of this adapter is produced through laser powder bed fusion on one of DMG MORI's own 3D printers. As you say, it simplifies the manufacturing process a great deal because you're not drilling those holes, you're not removing material to then put it back later. They're just building what they need to produce this part, with the exception that they do add additional features to make the post-processing easier. So there is a special part that we don't have here in the finished version that makes the vacuuming of the loose powder easier to do. After it gets vacuumed, it goes through heat treat, it goes through finish machining, and you end up with this final part. This component is lightweighted. It weighs about 8 kilograms versus the more than 15 kilograms that the original did. It's more reliable, it has fewer sealing points, and this is just a great illustration of additive manufacturing helping subtractive manufacturing.
It won our contest last year based on audience votes, our Cool Parts Showcase, in the category of Best Production Part, and it is a great production part, a great example of additive for production. They thought all the way through the production process to the extent of also finding a more efficient way to do depowdering.
So congratulations again to DMG MORI on your win. If you want to see our other episodes with showcase winners, you can find all of those on the channel or at thecoolpartshow.com. In the bespoke solution category, we had a wheelchair custom made for a dog, and in the best proof of concept category, a helicopter heat exchanger. They're both very cool and you should check them out.
If you have a cool part to share, maybe a component of your machine that you re-engineered for additive manufacturing, we would like to know about it. We might do an episode of the show about it. Email us, coolparts@additivemanufacturing.media.
If you enjoyed this episode, leave us a like, leave us a comment. If you have questions, let us know, and make sure to subscribe so you get notified about all of our new episodes. Thanks for watching.
This episode is brought to you by Carpenter Additive. We're past the point of not knowing how to qualify metal 3D printed parts. We know, it's just that different end users of those parts have different qualification requirements. Additive manufacturing service providers have to navigate that, and Carpenter Additive has to think about that in tailoring powder management solutions.
Our customers typically will have, if they are a service provider, they will have a series of end user customers who may be, say, OEMs in the aerospace world. And each of them has a fairly large team of engineers who've been doing this for decades or more and have developed all these standards, regulations, paperwork. So it is certainly a challenge to thread the needle between all of these different requirements. We start really high level, we walk on the shop floor, we ask them about, okay, source to sink, how do you bring in the materials, goods in, send that material to each of the systems, and then what we're really interested in is how do they reuse that material. So what we do is called a value stream map. Pretty often that leads to a series of things that were either overlooked or hadn't really boiled up to the surface yet in terms of things that are potential risks or potential challenges or inefficiencies that exist. A lot of the customers we work with, especially in the more regulated industries such as space or medical or aerospace, have already been through those early learning stages. They've put 5+ years into this. They've done the product design and the design for additive manufacturing. And now they're starting to reach some of the more finicky problems that you get when you're at the scale of maybe 5-10 machines. You're running different materials simultaneously, you're doing different programs. We get to take the best from the medical field and the aerospace field. We understand the specifications and the standards that exist in each of those fields, and we can sort of take the best elements of those and customize that to our customers.